Alright, you guys should know the vibes at this point. Chapter 12, I'm going to do a little bit of 11 at the end as well, but I think this chapter is not too tough as far as math goes. I think it's just the concepts here. Yeah, not too much, just a little bit of physics, but mostly algebra here. And if you understand your math concepts, this won't be too tough for you. So let's do it. So number one, we've got a gas that follows the PV diagram in the following figure. Want to find the work done on the gas along the paths AB, BC, CD, and ABCDA. So the entire thing, and then rather than put the point labels on there, but we're going to do top left to the right. Top left is A, top right is B, and then just along that path, and then back to where it started. So that's the idea, and I'm sorry I didn't put the labels on there, but now I'm going to go back and add them at all. So that's the idea. We've got a little bit of that. Find the work done. So we know that work is negative P delta V. The negative is just there as sort of like the statement. It's more of a convention thing than any math you're going to have to input. Be familiar with these, get comfortable with these, because you're going to have to see a lot of these along your chapter 12 homework. We've got point A, we're going to say in the top left, we've got a pressure of 5 times 10 to the 5th pascals. So you can write that. And we've got a change in volume of looks like 6 cubic meters. So we've got a change in volume of 6 cubic meters. So we've got that, and here's what I have written so far, just to keep you guys on the same footing as me. So we've got that, and we want to find the work done from A to B, right? So that's pretty simple. We can just do the math there. We're going to do 5 times 10 to the 5th times 6. That's actually really simple. It's going to be 30 times 10 to the 5th, so 3 times 10 to the 6th. But let's double check behind me. I might be doing really bad mental math. But yeah, 30 times 10 to the 6, or 3 times 10 to the 6. So that's pretty simple, and the idea here, we want the work done on the gas, so this is really important to consider. If the gas expands, the work done on it is negative, but if the gas is, so yeah, the gas expands, the work done on it is negative, but if the gas is doing positive work, so you want to make sure you're keeping a close eye on the wording there, but you want the work done on the gas, and it's going to be negative. So we got a negative 3 times 10 to the 6 to start for A to B. So do that really quickly. A to B is negative 3 times 10 to the 6. So from B to C, it's going to be that down arrow to the far right. We're going to go down 3 as far as pressure, and we've got a constant volume. And you guys should already get the idea here, but if you plug in a constant volume, you're going to have no work done. And you can just put the math in on your formula. You can put in 8 minus 8, but 0. So the idea is that if it's constant volume, no work's going to be done. So we've got AB, that's negative 3 times 10 to the 6. BC is going to be 0. Just going to write that as well. So work done at AB is negative 3 times 10 to the 6, and work done at BC is 0. Now we've got CD, right? So let's get a different color. CD, our pressure is 2 pascals. So 2 pascals, or 2 times 10 to the 5th. And then our volume is going to be we're going to have a change in volume of 8 minus 2, which would be actually 2 minus 8, which would be negative 6. 2 minus 8 is negative 6. I guess this is where your sign at the beginning could come into play. I usually just use the magnitude of the change in volume, and I just use the concept in my head because it's easier that way, and it's hard to mess up the math that way. Let's see, and I may have just accidentally removed a little bit of that, but yeah, I usually just go with the positive or the magnitude of the value, and I'll just do the constant in my head as to whether it should be positive or negative. So we've got 2 times 10 to the 5th times 6 as far as we're going to put into our formula. That should be 12 times 10 to the 5th, or 1.2 times 10 to the 6th. And since that gas is being compressed, right, work done on the gas is positive, so we're going to do positive 1.2 times 10 to the 6th. So we've got CD, and then you guys can work out ABCDA, right? So you can do that. Give you a second. And DA should be 0, right? So you've got 0 at DA, and that's because we have a constant volume, right? So this is what we have in total. You want ABCDA, right? So the whole thing. And we're just going to put these values together. So we've got negative 3 times 10 to the 6th plus 1.2 times 10 to the 6th. We can do that math in our head, that's not too tough. We're going to get 1.8 times 10 to the 6th as our final value for work. So not too tough at all. Yeah, the main idea here is just knowing your concepts and knowing your work formula, work equation. But yeah, not too tough at all. Let's move on to the next one. Okay, so here we've got chemical reaction transfers 7,000 joules of thermal energy into 17.5 moles of an ideal gas, while the system expands by 2 times 10 to the negative 2 cubic meters at a constant pressure of 2 times 10 to the 5th pascals. We want to find the change in the internal energy and calculate the change in temperature of the gas in kelvins. So first, let's write what we have. That's always a good place to start, what we have, and we can find what we need, and see what we don't have type deal. So cubic 7,000 joules thermal energy. Oh, so yeah, variable for that was Q. That's what gave that away, but now you know. I was going to ask you to find it yourselves, but I guess it's easier if I just tell you Q is what the variable there for the thermal energy we're going to put in there. 17.5 moles, you could find that variable yourselves. So 17.5 moles of an ideal gas, just a hit there. While the system expands by 2 times negative 2 cubic meters, so we've got this gas expanding, so think about that. So what variable is that? 2 times 10 to the negative 2 cubic meters going to be. We've got constant pressure, which is another hint, of 2 times 10 to the 5 pascals. And we want to find the change in the internal energy. We want to calculate the change in temperature of the gas. So looking for change in internal energy and change in temperature. So you should know, if you watch this Spino's video, what the change in internal energy variable is going to be. And I told you what Q is. So let's just show you what I have, and hopefully you've got the same thing, right? So we've got Q, we've got N for the moles, we've got delta V for the change in volume, we've got P for pascals, it's capital P. We've got delta U for the change in internal energy, we've got delta T for the change in temperature. So that's what we're working with here. So take a second to consider what we're going to use to find first the change in internal energy. Right? So how are you going to find delta U? And if you look at your formula sheet, there's not many options there. So you should get this easy, right? You should get delta U equals Q plus W, right? So that's Q is going to be like the heat we're going to transfer, or energy we're going to transfer, or input rather, maybe. And then W we know is work. If you add the heat we're going to input or transfer along with the W, which is work, you would get the change in internal energy. So that's the idea. We realize we don't have work just yet, so we could find it, right? So how are we going to find the work? Take a second, I'll go ahead and put a little bit on my board. And you should have settled on work equals negative P times delta V. The pressure is going to be 2 times 10 to the 5th. You plug that in. Pascals. Delta V is going to be 2 times 10 to the negative 2 cubic meters. So we've got 2 times 10 to the 5th times 2 times 10 to the negative 2. That should be 4 times 10 to the 3rd. Let me double check my calculations because you never know, maybe I'm off today. And yeah, 4 times 10 to the 3 or 4,000. Probably a better way of wording it. 4,000 joules. So we've got 4,000 as our work. Good plug it up there. And we already know what Q is, right? The 7,000. So we've got a transfer of 7,000, and we've got an expansion of 4,000. So the expansion is going to be positive, and expansion is going to be negative, and then the transfer is going to be positive. We're inputting 7,000 to the gas, right? So 7,000 is positive, and the 4,000 is negative. So that's the idea here. It's tricky with the wording. You want to pay a lot of attention to the wording in this chapter. So delta U equals 7,000 minus 4,000. The 7,000 is the Q. We're going to input the 7,000 to the system. The gas is going to work on the system, and it's going to expand with a work of 4,000. So we're going to subtract 4,000 from the 7,000. And that's pretty easy math there. 3,000 is our change in internal energy. So I've got that. We can put that to the side. So you really want to pay attention to the wording with these. Wording is the main idea here. Like the math is very basic. The concepts aren't rocket science by any means. Not that rocket science is too crazy. But got that. We want to find the change in temperature as well, right? So take a second to consider what we use to find the change in temperature. I'll go ahead and write a little down. And by the way, your change in internal energy would also be joules, in case you're running a variable for that. But the math would have told you that as well. So you want to find how to calculate change temperature. So you should be familiar with this concept that was touched in chapter 11 and 10 as well. You should settle on P equals nRT. Is that up there? Yep, P equals nRT. And you know that R is a constant, so not too tough there. And it tells you specifically you want to find the answer in kelvins. You're only going to have R in kelvins, so that's the idea. If you have R in kelvins, you don't want to use Celsius for your calculations. So P equals nRT, our pressure is 2 times 10 to the 5. Our volume is going to be, let's see, I'll sneeze. So Volume is going to be 2 times 10 to the negative 2 equals, let me erase a little bit, get some space going. So yeah, pressure is 2 times 10 to the 5, volume is 2 times 10 to the negative 2. N is going to be our moles, right? So N is going to be 17.5 moles. R is on your formula sheet, 8.31. And then T, right? So I've got just PV and RT in number form. That's it right there. It's just PV equals an RT. So you do a little math there. Take the time to do the algebra here. I'm getting a temperature of 27.5. Let's double check that as well because I didn't do this problem yet. 27.5. That makes a lot of sense. Yeah, exactly right. So 27.5 kelvins is your answer, which feels pretty low. But that's what we got. So that's the idea there. The main thing is knowing your variables here. But as you saw, the math isn't hard at all. The math is not complicated here. But yeah, know what U is, know what Q is, know what W is, which you already know. And that's the main thing here. Know what your variables are. So let's get to the next one. So this one's really similar to the first one we did. We've got a gas increasing pressure from 3 atmospheres to 9 atmospheres at a constant volume of 1 meter cubed, and then expands at constant pressure to a volume of 6 cubic meters before returning to its usual state as shown in the figure. So essentially what we have in the figure here, how much work is done in one cycle. We're going to solve it the exact same way we did with the first part, or the first question. So let's get right to it. I think this concept is pretty straightforward. We look at it more as just finding areas of triangles and rectangles. So let me actually draw this on my board. So if we're looking for that one main triangle, right? Draw this better. Looking for that one main triangle, which is right here, right? Well, you realize we've got a full rectangle that is consisting of, or as a part of, right? So you've got that triangle, and it's made up of another triangle and another square. Let's see, another rectangle rather. So we've got that triangle on the find at the top. We've got a triangle right under it, and a rectangle beneath both of those, right? So yeah, we're going to work with just areas. When we look at these as just areas of triangles and rectangles. We're going to do a little bit of what we did in the first problem, and we're going to find the values of these paths, A to B, B to C, and C to A again, and that would be the triangle. But once we find those, we won't really be finding C to A. We're going to just subtract the triangle beneath it and the rectangle beneath both of those. So by that logic, you can look at B to C, that top row from left to right, and you could figure out that will represent what. Maybe that's not the right wording, but what would that value be as far as areas? And you would think that that would be the area of that full triangle or full rectangle that I drew. So if we found B to C, that would give us the full area of that rectangle. Let's get a little more clear. So B to C is the top of that rectangle. Our height is going to be 9, and our base is going to be 6 minus 1, which is 5, right? And that will give you your full rectangle. That's what I mean by that. B to C is going to give you that full rectangle. So we're going to subtract from that rectangle the triangle above it and the small rectangle at the bottom. So not too complicated. I guess maybe I may have worded it sort of weird, but the idea is pretty simple in general. You just want the area of that one rectangle at the top. So let's find B to C, right? You should know how to do that, so let's do it together at the same time rather, and we'll meet together as we finish, as we get to the answer. So work from B to C, and this is a gas that is expanding. So we want to see how much work is done. We're going to say that the expansion, we're going to say that it's work done by the gas, so the gas is doing positive work. And the wording is always something you want to focus on, make sure you got correct, but yeah, it's going to be positive here, I feel like. So work here is going to be, so our pressure is going to be the 9. It's an atmosphere, so we're going to have to multiply it by our conversion rate, which would be 101,325. And our change in volume is going to be 6 minus 1, which is 5. So this is what we're looking for B to C. And we can get our answer, do a little math in the calculator. And I'm getting 4,559,625. So let's see. I'll just erase a little bit of that. I'm getting 4,559,625 joules. So that's what you should be getting for B to C. 6 times 1. Yeah, okay. So we've got the area of the full rectangle, right? Let's get rid of that triangle in the middle next, right? So we're going to subtract work of that triangle, or the area of that triangle. We're getting negative P delta V, right? I'll show you that. Pressure here, or our height, would be 9 minus 3. Do we see that? 9 minus 3? It's 9 minus 3 here because the top of the triangle is at the 9, the bottom of that triangle is at the 3. And that's a good way of helping you visualize that as well. So we've got 6 4-hour pressure. We're going to, of course, multiply by the conversion rate, which is 101,325. And our volume is going to be the base of that triangle, which is going to be 6 minus 1 again. So 5. So let's do that math, and let me show you actually what we have. 6 times 101,325, and then that times 5. Let's do that. I'm getting 3. Oh, so I almost made a mistake, but you may have caught it yourself. This is a triangle, right? So we're going to do 1/2 of that. The area of a triangle is 1/2 base times height. We're going to do 1/2 of our base, which is our change volume, and our height, which is our pressure. So we're going to do 1/2 6 times 101,325 times 5. So we're finding the area of a triangle here. So let's do that again. And you should get exactly half of your answer, which is 151. It looks like 1,519,875. Put that there. Of course, you're going to subtract that. So 1,519,875. And of course, we're still working with joules. So make sure you are using your algebra, maybe area rules. I'm not sure if that's a thing, but working with areas. Area of a square or rectangle is going to be base times height. Area of a triangle is going to be 1/2 base times height. And that makes it so much easier. Now I want to subtract that rectangle at the bottom underneath everything. So we're going to do work equals negative pressure times delta V again. Pressure there is going to be 3. And of course we want to put in our conversion rate as well, so 3 times 101, 325. Delta V is going to be 5 again, so not complicated there. As we're looking at, let me put a little drawing over there as well. So we've got that. Do a little math, it shouldn't take you long. I actually think it's going to be the exact same as what we just did. And yeah, exactly the same. So we're going to do minus that same value again. That's just how it works out. So that's what we've got. We've got 4 million, we're going to subtract about 3 million. And our final answer will be whatever we get. So let's do the math there. I'm just going to do pink plus blue plus maroon. So those values, we're going to put them all together. And now I'm getting the same value as what we just got for the last two. Because apparently what we found for BC is exactly 3 times that value. So we're going to get our final answer. Let me get a marker. Final answer is going to be 1,519,875 joules. So yeah, I tried to make these problems sort of convenient numbers wise, and I did a really good job today. Not very complicated there, just want to make sure you know how to find your areas. You can keep that in mind. Of course, you know your work equation. Otherwise, not too complicated at all. Sort of building on that first problem we did. So make sure you can read these graphs well, make sure you can calculate well with these graphs, and you'll be fine with that concept. So for this next problem, we've got the work done by an engine equals 1/8 the energy it absorbs from a reservoir. We want to know what is the thermal efficiency, and we want to know what fraction of the energy is absorbed, is expelled to the cold reservoir. So here's where you just want to be familiar with your formula sheet again. You want to be familiar with your formulas and your variables. So I want the engine efficiency. What is the thermal efficiency? Look at the formula sheet and you should be able to find what that is. Shouldn't be too tough. We also know that work done by the engine equals 1/8 energy absorbed from the reservoir, and you should know a few of those ideas there. So the work done is 1/8 of the energy it absorbs from the reservoir. So maybe you know what that is. But here's what I have just to show you. E is our efficiency, work is our W, 1/8 of our QH. That's going to be your energy that you input to the system. So you're inputting 1/8. Oh no, work is going to be 1/8 QH. So we know that. We can solve. What is thermal efficiency? So it'll list your formulas, and I'll let you think for a second to find what you want to use. And you'll notice we have work, we've got QH essentially, and we've got E, right? And there's only one formula that uses all those, right? There's only one formula that uses all those, right? And it's going to be the E equals work, the engine over QH. And hopefully you saw that. Work is going to be, we're going to say it's essentially 1. And no, we're going to say it's 1/8. And we know that Q is 1, right? So work done by an engine equals 1/8 the energy it absorbs from a reservoir with thermal efficiency. So that's easy math there. 1/8 over 1 is 1, right? So the answer is 1/8. What maybe they wanted in a percentage. So you could have said 0.125 as well, or 12.5%. However you want to put it, but not complicated there. Next question is what fraction of the energy absorbed is expelled to the cold reservoir? So this isn't complicated either. If you have been following the chapter and you've watched Spino's video, take a second to find what formula you want to use, and we will congregate, I guess. So what fraction of the energy absorbed is expelled to the cold reservoir? You should have chosen this equation or formula to use to solve. So just based on what we said with the previous step, work is going to be 1/8. QH is going to be 1. You're going to do minus QC. QC is the energy that the cold reservoir is going to get. So this is really simple as far as math goes. Like I've been saying, this isn't the most math-intensive section. 1 minus QC equals 1/8. QC has to be 7/8, right? So the answer for the fraction of the energy absorbed that's expelled to the cold reservoir is going to be 7/8. And that's not too tough at all. So may have flown through that, but hopefully you got the idea. QH is going to be your energy that the system takes in, and it's going to expel a certain amount of energy. That expelled energy is going to be the QC. And of course, you know what work is. So yeah, just a little bit of concepts there. Not too tough. Maybe I'm not explaining the best. I feel like I rushed a little bit. Feel free to leave a question if you want. Email me. But yeah, if you know this concept, this wasn't too tough for you. So here we've got a very efficient engine that operates between 1,760 degrees Celsius and 400 degrees Celsius. Want to know what is its maximum theoretical efficiency, and then we also want to know if its actual efficiency is 38 degrees, or 38% rather. How much mechanical power does the engine deliver? It absorbs 1.6 times 10 to the 5th joules of energy each second from the hot reservoir. So this one isn't too tough at all. We want to find its maximum theoretical efficiency. If you've been keeping up with the chapter, you should know that is a Carnot engine efficiency. In theory, Carnot engine is the most efficient an engine can be, but that's all theoretical. But the idea is we can solve it. We can figure out exactly what that value would be. We got the formula sheet down there. The formula should be pretty self-explanatory. It says E Carnot, efficiency of the Carnot engine, and yeah, the TH and TC should be pretty explanatory or self-explanatory as well. But let's just do it ourselves, and I'll come together with you guys, and hopefully we got the same thing, right? So 1 minus TC over TH. Back to the numbers. We've got 1760 and 400. We want those in kelvins for our calculations, so make sure you're using kelvins when you're solving these, right? So we're going to do Little math. Yes. And for my efficiency, I'm getting a theoretical efficiency of 66.9%. So you notice I used low temperature for TC, I used high temperature for TH. I of course converted those to kelvins, and yeah, not too complicated there. Should be able to do that with no trouble. That part is not too tough at all. You just want to make sure you're using the Carnot, your Carnot values or your Carnot equation to find the efficiency of your maximum theoretical efficiency. Next part, we want to know its actual efficiency is 38%. How much mechanical power does the engine deliver? It absorbs 1.6 times 10 to the 6 joules. So it's absorbing 1.6 times 10 to the 6 joules, and we want to know how much power does the engine deliver. So I guess we want to find work. Let's actually write this down. So efficiency is 38. It absorbs 1.6 times 10 to the 6. We're going to call that Q. We're going to call it QH. What is Q? We're going to see. Freestyle this one. What power, right? So essentially just going to find the work. So efficiency equals work. Okay, yeah, this is QH. So we're going to use the efficiency equals work over QH formula. You should see that this should be your first efficiency equation. So that's not too complicated. Finding that. Here, like I said again, you just want to know what your variables are. You want to read the questions very carefully. You want to be able to read into the questions and decide what you want to use, what you want to find. But as far as math, this section is not complicated at all. So like I said, we're going to use efficiency equals work over QH. They gave us the efficiency, so it's going to be 0.38. QH is 1.6 times 10 to the 6. And we want to find the work to find the power, right? Here's what we've got. It's the same thing, just efficiency equals work over QH. Multiply both sides by QH to get rid of that. So we've got work equals 1.6 times 10 to the 6 times 0.38. I'm getting 608,000 is our final answer. 608,000 joules for work. You want to know what power? Let me say that per seconds would be our power. So we're going to say our power is going to be 608,000 joules per second or 608,000 watts. That's not too tough at all. So yeah, make sure you familiarize yourself with the formula sheet. A lot of it is just very apparent as far as solving. So you know the formula sheet very well, you know the concept very well, you can just sort of figure it out as you go. You can sort of read into the formula sheet and put it all together. Of course, you know power is watts is joules per second, and it's going to be work per unit time. So the power that the engine delivers is going to be that work you found per seconds. Not too complicated there, and yeah, good question. Alright, here you've got an engine that absorbs 1900 joules from a hot reservoir at 300 degrees Celsius and expels 1300 joules to a cold reservoir at 30 degrees Celsius in each cycle. We want to find what is the engine's efficiency. That's not too tough. We also want to know how much work is done by the engine in each cycle. And you also want to know what is the power output of the engine if each cycle lasts 0.390 seconds. So let's look at that first part. Let's just write out what we have first. It's always a good idea to put out what you have and what you don't have. So engine absorbs 1900 joules. So what variable is that the engine absorbs? Your times, write that out. If you don't know, pause and find out what it is. The temperature there, the high temperature is going to be 300 degrees Celsius. Expels 1300 joules to a cold reservoir. So what value is that going to be? What variable are you going to use? And that's going to be 1300 joules. 30 degrees Celsius is going to be our low temperature. And that's all we're given. But we want to know what is the engine efficiency. Right, what variable that is. And find it. Here's what I have as far as what we have and what we don't have. QH, our high, or Q, our energy that we absorb is going to be 900. TH is going to be our high temperature, it's going to be our 300 degrees Celsius. The energy we're going to expel is going to be 1300 joules, QC. TC is our cold temperature, it's going to be 30 degrees Celsius, and E is our frequency. Not too tough. Let's do the math a little bit. Take a second to find what equation you want to use. And we're finding the efficiency, right? So we're going to do a little math. And you should have settled on, maybe use something else, but I settled on this one. Efficiency equals 1, and it's over here, 1 minus QC over QH. 1 minus QC over QH. So we can plug in our values really quickly. 1 minus QC, which is 1300 joules, over QH, which is 1900 joules, give us our efficiency. Take your time to put that on the calculator. We're getting 31.6% is our efficiency. Or 0.3157, so 31.6%. And that is the first part. Not too complicated there. You've done it a million times, hopefully. Pretty simple stuff. So our efficiency is 31.6%. Next part, we want to know how much work is done by the engine in each cycle. So that's not too complicated. We just want to find the work, right? So we know how much energy we input and how much energy we expel, right? We also know our efficiency, right? So let's settle on what we want to use to solve this part of the problem. So take your time. Actually, you may settle on something else, but I'll settle on this. The work equals QH minus QC. Of course, we already know that QH is 1900. QC is 1300. So work should be 600, right? RT minus 1300 is going to be 600. So 600 joules. Much work is done by the engine each cycle. So yeah, 600 joules each cycle. What is the power output of the engine if each cycle lasts 0.390 seconds? This isn't very complicated either. Power output we know is going to be work per second, or work per time rather. So power work per time. We know what our work is. We know what our time is, the 0.390. So we're going to plug in work and time into those variables, into our equation. We know our work is going to be 600. Our time is going to be 0.390. Let me show you guys this as well. So to be totally sure you got what I got. So 600 divided by 0.390. I'm getting 1,538. 1,538. And what's your unit here? Watts. So 1,538 watts. And that is that on that. This isn't a very tough problem at all. Like I said, you just want to be sure you know what you're using here. Know the concepts, know the variables. This chapter, in my opinion, is maybe one of the easiest you'll see, or we have seen, because it's the end of the year, but not too tough here. Just know the concepts. Here we've got, in one cycle, a heat engine absorbs 500 joules from a high temperature reservoir and expels 300 joules to a low temperature reservoir. If the efficiency of this engine is 55% of the efficiency of a Carnot engine, what is the ratio of the low temperature to the high temperature in the Carnot engine? So just build on the last few we've done. Again, not super math intensive. Just want to know a little bit of algebra and you can do this with little to no trouble. One cycle, it absorbs 500 joules. So write down what that variable is and the number 500 joules. Expels 300 joules to a low temperature reservoir. So write that variable and the joules, 300 joules, of course. The efficiency is 55% of the efficiency of the Carnot engine, so we can write that. Efficiency equals 55% of the Carnot. Let's do that. Efficiencies, 55% of the Carnot, that'll work. Let's make this clear. 55% of the Carnot, and that is all the information we have. We want to know what is the ratio of the low temperature to the high temperature in the Carnot engine. So, interesting question. We want to find TC over TH, right? Here's what we've got, what we want to find. QH, the energy that we put into the system. QC, the energy the system expels. We know that the efficiency of the system is 0.55% of that of a Carnot engine, and we want to know what the ratio is of the the low temperature over the high temperature. So first thing we want to find is the efficiency, right? If we can find the efficiency, we can plug it in, find the efficiency of the Carnot engine, and then find the ratio, right? So we want to find the efficiency. We've got the input energy and we've got the expelled energy, right? So settle on what you want to use to find the efficiency with those values, right? So we're going to take your time to find what you want to use. I'm going to settle on, I'll show you actually. I'm going to settle on 1 minus QC over QH. I may have used a different one, but this is the one I'm going to use. It's just a little bit of not a lot of work, if that makes sense. A little bit of not a lot of work. QC is going to be 300. QH is going to be 500. 1E. So we've got efficiency should equal 1 minus 300 over 500. Minus 300 over 500. You should get 0.4. 0.4 is our efficiency, or 40%. So 0.4 or 40. Did I get that? Yeah, 0.4 or 40. So we know our efficiency is 0.4. And we know that that is 0.55% of what the Carnot engine could be. So 0.4 equals 0.55 the efficiency of the Carnot engine. So that's what I have. 0.4 equals 0.55 the efficiency of a Carnot engine. So we want the efficiency of the Carnot engine. We're going to do 0.4 over 0.55, right? A little algebra there. And once we do that, let's erase this as well. We do that little math, we should get the efficiency of our Carnot engine should give us 72.7% or 0.727. So that's what I'm getting for our Carnot efficiency, which is really good, which is crazy. We've got that. Now I can plug that into the equation for the Carnot engine, right? That's just a little math there. 21 minus. That's how we find the efficiency of the Carnot engine. We know that that efficiency is going to be 72.7, right? Should plug 72.7 in there. And our rest actually going to be 0.727 equals 1 minus that ratio we're looking for. So that bottom step right there, 0.727 equals 1 minus the ratio we're looking for. Or you just move things around a little bit. That ratio should be should be 1 minus 0.727. So not super tough there. Answer would be 0.273. So our ratio, I'm going to write up top, 0.273. Erase this. So not too tough there. And that is all we're looking at there. So we really did the same problem like 5 times. This section or this chapter, like I said, it's not super math intensive. Just want to know the concepts. Make sure you know your variables. Make sure you know your concepts. But yeah, the meat as far as solving problems and concepts is going to be 10 and 11 if you ask me. So of course, know these concepts, but if you're familiar with the formula sheet, not too tough. And that's it. We're going to focus on one more problem. So let's look at that. So this one, chapter 11 concept. I wanted to focus on this problem because it's the part B of the problem we did to finish the last video. Not too tough if you understand the concept, sort of just another direction. So we had, with the last problem that we did that I'm referring to, we had a large amount of steam and a small amount of ice. The steam melted all the ice, and that was the idea. Here we've got a small amount of steam and a large amount of ice. So we're gonna melt some ice, but not all of it. So let's actually just do this. So of course the steam is at 100 degrees Celsius. Ice at 0 degrees Celsius. Let me just write that down. You want to find the amount of ice that's melted and the final temperature when the mass of steam is 9 grams and the mass of ice is 90 grams. So mass of the steam is 9 grams, mass of the ice is 90 grams. You know me, I like to use the calorie per, calorie gram values. So we're going to use those. It's a little easier as far as math goes and better looking numbers as well. So we've got that. So like we started the last problem, or the first part of this problem, the idea is that we're going to use the values to find exactly how much steam's going to condense and how much how much we need to melt the ice. So I may have said that weird, but the idea is that we're going to use latent heat diffusion to find how much energy we need to melt the ice, and latent heat vaporization to find how much energy we need, or how much energy the steam is going to release when it condenses. We're going to use that to find exactly how much ice is going to melt before we do any serious work here. So we can do, and actually I'll show you what I have first. This is what we have, and it's just the basics. Everything else on the formula sheet, so be familiar with that. It's something that I actually added, but you should get that on your exam as well. So mass of steam is 9 grams. Latent heat of vaporization, or latent heat of fusion rather, or vaporization rather, is 540 calories per gram. So we could do 9 times 540 equals the amount of energy that steam is going to give off when it condenses. So 9 times 540 is the latent heat of vaporization for water or steam, and we've got the mass, and we're just going to find out how much energy that the steam is going to release when it condenses. So 9 times 540 gives us 4860. 4860 calories going to be released by the steam. So same thing with the ice. But we're going to use the latent heat of fusion. So we're going to do 90 times 79.7. And I'll show you that as well. Do a little math there. Should get 7173. And that is how much energy we need to melt the ice. So we need 7173 to melt the ice. And the steam release is 4860. So I just wrote that down. And off that you realize that we don't have enough steam to melt the ice, right? So we don't have enough steam to melt all the ice. We're left over with a big chunk of ice. So left over with a big chunk of ice, what temperature would that be? If it started at 0, what temperature would it be now? And in theory, it'd still be 0, right? So that's a little bit of a easy gimme type part of that question. Temperature there is going to be 0 because we still got that chunk of ice. So write that right there. Temperature's going to be 0. We just want to find how much ice melted. So the steam condensing gives off 4860 calories to melt some ice, but it's also the condensed water is gonna react with the ice as well. So that water is gonna have to get to 0 degrees, right? So we're gonna do MC delta T, a little MCAT. We're gonna find out how much energy we get if that 100 degree water goes to 0 degrees, right? So we've got 100 degree steam, or 100 degree steam, we've got 100 degree steam, turns to 100 degree water, 100 degree water is going to react with that 0 degree ice, meet at the equilibrium point, right? So we can plug in our values. We still got the 9 grams for the mass. This is water now, right? So we're going to put in the 1. Change in temperature is going to be 100, right? So here's what I've got. So 9 times 1 times 100 is 900. So we put that with the 4860. Let me just slow down a little bit. We just found out that the water cooling down is going to give off 900 calories. So I put the 900 calories with the 4860 calories. Calories as well. So we've got our calories inputted over here. So get our sum there. So 4860 plus 900. Should get 5760. So erase a little bit. And you've got 5,760 calories given off by the steam condensing and the water cooling. So we've got 5,760 calories to melt the ice. So we have an energy, we have some other values. We want to find how much ice melted, right? So take a second to think about what you'd use to find how much ice melted. And you should have settled on the latent heat of fusion formula. So we've got our energy given. We want to see how much ice that can melt, right? Latent heat of fusion, of course, is going to be the 540, or 79.7 rather. Sorry about that. So we're going to use 79.7 as our latent heat of fusion. We're going to divide both sides, of course, basic algebra from there. And we should get a mass of 72.3 grams. 72.3 grams. So 72.3 grams of ice is going to melt. That's the idea there. It's the second part of that question we touched last week. Not too complicated if you know your concepts, but the idea here is if all the ice doesn't melt, you're going to have 0-degree ice. You're going to work for the mass. Part A, if all the ice melts, you're going to have no ice left, and you're going to have to find the temperature that we finished at. So not too complicated, just want to make sure you got both sides of that question. Otherwise, not very difficult, just very different. So that's it for that. So with all that done, we should be good on this section. Not the most difficult, of course. Very concept intensive. You really want to be focusing on what you're doing exactly. Like I said, it always helps to visualize and always helps to write down what you know, and your brain will help you through it. Yeah, we rushed through that a little bit, but not the most difficult. Like I said, if you get a lot of practice here, you'll be pros. Next week, we're going to do more of a full final exam type prep. Yeah, make sure you know how to do your equilibrium problems, your temperature problems, and that's it. Hopefully you've got chapter 12 down pat with this video. Again, like I said, it's not very tough as far as math goes, just very concept intensive, and that's it. Feel free to email me, of course, and have a good break.